Hi, this is lecture 2.7 of the Sage-based course on Monte Carlo Methods. In the last video, we just formally saw the definition, axiomatic definition of probability. Now we're going to do some probability examples. So example 1 is tossing a fair coin. Here the sample space is h, t, capital omega is h, t, and the probability that the coin lands heads, P of h, is the same as the probability that it will land tail, which is P of t, and it is 1 over 2, 1/2. So it's a fair coin. Now let's check that all our axioms are satisfied. So axiom 1 is clearly satisfied because the probability of h is probability of tail, and it's half, and clearly is between 0 and 1. Half is between 0 and 1. So we're good. Now, probability of the entire sample space, the second axiom, is the probability of h and t, which is the probability of h plus the probability of t, and it's half plus half, and that is 1. Like we wanted. We wanted something in the sample space to happen. So that's P of omega is 1. Axiom 2 is also fine. Now what about axiom 3? Probability of h comma t, okay, is, there should be a close parentheses here, it's a typo. So probability of h comma t is probability of h plus probability of t. Sure, h and t are disjoint events because h intersection t is the empty set. So the probability of h comma t, or either h or t happening, is the probability of h plus the probability of t. This is also true. We don't have to really worry about axiom 4 because there are only finitely many elements in capital omega here. Example 2, the New Zealand Lotto. In New Zealand Lotto, the balls drawn are numbered from 1 through 40. So the number on a ball is an outcome. So then the sample space is the set 1, 2, 3, up to 40. And probability of little omega, so this is little omega, okay, probability of little omega is 1 over 40, and little omega can be any element of our sample space. So little omega can be 1 or 2 or 3 or any number up to 40. So all of the balls have the same probability, 1 over 40, of coming out in the first lotto draw. Okay, so probability of 1 equals probability of 2, equals probability of 40, which is equal to 1 over 40 in this well-stirred urn of lotto balls. Now consider the event that the first ball is even. It's an even number. What is the probability of this event? So clearly an event is a subset of the sample space, so we only take the even numbered balls, 2 through 40, right? So 2, 4, 6, 8, and so on up to 38 and 40. So the probability of even is simply probability of 2 union 4 union 6. This is simply the definition of set union, right? So now that is equal to probability of 2 plus probability of 4 plus probability of 6 all the way to probability of 40. So this is just extended axiom 3. So the union of a collection of disjoint events, its probability is simply the sum of the probability of each event. Well, we simply add them. Well, this is just a summation, P of I. So this is just adding all these even numbers, the probability of all these even numbers. And there's 20 of them, so this sum is simply 20 times 1 over 40. Because there are 20 items of probability 1 over 40 that we are adding. And that's just half. So this whole thing here is just saying that the probability of the event that the first ball that comes out of the lotto machine is an even numbered ball is just 1/2. Similarly, for the probability of an odd ball, we just go through the odd balls and discover that that's also 1 over 2. So either an even ball or an odd ball can come out with equal probability from the lotto machine. Let's look at the Waimakariri urn. So the Waimakariri is a beautiful river that runs, a braided river that runs north of us in Christchurch here. So imagine taking the letters that make up Waimakariri and throwing them into an urn or a little box with all the letters in it. So the game is to sort of mix up this urn and pull a letter out. So the sample space, capital Omega, for the Weimakariri urn is capital Omega. It equals little omega 1 is W. Okay, so W is one of the letters, so we sometimes use the little omega 1 to talk about explicitly maybe the first element in our set of outcomes, or the sample space. Little omega sub 2, or omega 2, is the letter A. Little omega 3 is the letter I, and omega 4 is M, and 5 is K, and omega 6 is R. So we have 6 outcomes. So one of these 6 letters can be pulled out of the Weimakariri urn of letters that make up Weimakariri. Probability of W, the first one, is 1 divided by 11. Okay, why is that? Okay, think about the urn here. So in this sort of representation of the set, there's W. There's only one W in Weimakariri. Okay, so, and there are 11 letters in Weimakariri. So if the probability of drawing a W is just 1 out of 11, right? But there are 3 A's and 3 I's, so the probability of drawing an A or an I is 3 over 11. So what you're looking here is the probability map that's assigning each value or each event or an element of the sample space to a number between 0 and 1. And M and K again are just like W, and they only occur once in the word Weimakariri. So this should be clear. Now let's consider the event that the letter we draw is one of W, A, or R. That is, we're now only interested in the event that one of these 3 letters, W, A, or R, is pulled out of the urn when we do this experiment. So we put these letters in, shake it up, and then we're going to draw one of these letters. So the problem here is on the left side, this expression is saying what is the probability of getting either W, A, or R out. So okay, so that's just the probability of W union A union R, and these are pairwise disjoint events. So this is simply the probability of W plus probability of A plus probability of R by axiom 3. So we simply sum up the probabilities and get 6 over 11 for the probability of the event that we pull either W or A or R. So here's an aside for those of you who are a bit more mathematically inclined. The set of all possible sets of the sample space is called the power set and is denoted by 2 to the power of omega. The power set is called a sigma algebra or a sigma field. We might talk about this more later. Now, having introduced a number of definitions, we will derive some basic logical consequences or properties of these probabilities that have been defined axiomatically. So property 1 says probability of A is 1 minus probability of A complement. Okay, what is A complement? A complement is nothing but the set difference of the sample space and A. So A complement is the set of all outcomes in the sample space that are not in A. So property 1 is simply that probability of A is 1 minus the probability of A complement. You can go through this proof yourself and understand why that property is true. Example 4. In the coin tossing experiment omega with head and tails, probability of H is 1 minus probability of H complement. So this is again demonstrating that that property holds for our coin tossing experiment. So probability of H is just 1 minus probability of H complement, which is tail. Property 2 says for any two events A and B, probability of A union B is simply the probability of A plus probability of B minus the probability of A intersection B. Okay, the proof was sort of by picture here. It's here is A, some set with some outcomes in it, and here's a set B or an event B with some outcomes in it. And this is A intersection B, which is the event that A and B occur. So in this informal proof using the picture above, if we just add the probabilities of A and B, we will double count the probabilities of the outcomes which are in both A and B. So we adjust for this double counting by simply subtracting probability of A intersection B. That's all that's going on here. Okay, so property 2 simply is again a consequence of the axioms 1, 2, 3, and 4. So now note that if A intersection B is the empty set, then probability of A intersection B is 0, and probability of A union B is simply probability of A plus probability of B, which is just our addition rule from the axioms.